Okay, let's unpack this.
Right.
Today, we're doing a deep dive into what is, I think, arguably the single most important strategic document guiding the global automotive industry's next 2 decades.
I'd agree with that.
We're analyzing the Efficient Powertrains Special Technical Roadmap 3.0. And this isn't just some technical guideline for engineers.
No, not at all.
It really reads like a high-stakes, comprehensive consultancy report, a blueprint for achieving total global powertrain leadership by 2040.
That's the critical distinction we have to make right at the outset. When we examine a plan with this kind of depth, spanning hybrid gasoline systems, pure electric components, and even heavy-duty diesel and natural gas engines.
It's everything.
It is. We have to recognize it as a declaration of national strategic intent. So our mission here is to decode this plan, to really understand the sheer ambition behind its quantitative goals.
And there are a lot of them.
A lot of them. And we need to analyze this systematic architecture that's designed to transition an entire sector from being merely world-class, which, frankly, they have largely achieved, to being the undisputed global leader.
And what gives this 2040 vision its driving urgency? I mean, it's not just about selling more cars, right? It's driven by 3 monumental top-level challenges that really form the foundation of this whole roadmap.
Yeah, and they're all inherently interconnected. They reflect the most significant policy pressures on the economy.
So what's the first one?
The first is rigorous support for the dual carbon goals, carbon peak and carbon neutrality. The roadmap is very pragmatic about this. It acknowledges that to achieve these targets, you need flexible solutions.
Meaning pure EV isn't the only answer.
Exactly. It's not the single, immediate solution for every region or every type of vehicle. So therefore, highly efficient hybrid and efficient combustion technologies have to coexist and evolve aggressively in parallel.
Right, so it's a pragmatic strategy. It acknowledges the reality of diverse global energy infrastructure, varied regional maturity levels in grid reliability, charging networks, all of that. It's not an all-in bet on batteries.
Precisely.
Yeah.
Which leads to the second imperative, and this is maybe the most existential one, energy security.
Okay.
By driving toward the full hybridization of all traditional energy passenger vehicles and getting these massive system-wide efficiency gains in commercial vehicles, the strategy aims to heighten overall energy utilization.
Which in turn reduces reliance on any single energy source.
And specifically, imported petroleum. The efficient powertrain becomes this foundational tool for energy diversification and strategic resilience.
And the third imperative, that one ties directly to geopolitical and global economic power.
It does. It's about enhancing the automotive industry's international competitiveness. This is the strategic payoff.
This is the end game.
It is. It's about leveraging these technological breakthroughs in thermal efficiency, in innovative hybrid transmission designs, intelligent energy management, to bolster the entire industry's core competitiveness. The ultimate strategic objective here is really the cementation of global leadership through globalization.
And by globalization, they mean having the intellectual property and the core tech that actually dictates international standards.
And secures market share worldwide. We are looking at a plan for industrial sovereignty.
So let's establish the current baseline then. Before we can talk about 2040, we need to know where this effort is starting from. And the entire plan is framed around this robust dual architecture.
Yes, and the architecture is designed for redundancy and flexibility. It's built on 2 parallel tracks: the efficient hybrid powertrain and the efficient non-hybrid powertrain.
Okay, so one for hybrids, one for everything else.
Sort of. This technical decision supports the long-term goal of getting comprehensive hybridization for traditional passenger vehicles by 2040, while at the same time pushing conventional heavy-duty engines to their absolute thermodynamic limits.
So the core belief here is that all these different powertrain routes have to coexist.
It's non-negotiable. Whether that's a hybrid electric vehicle, a range-extended EV, or a pure combustion system, they must coexist and dynamically adapt to different regional energy structures, infrastructure maturity, and specific market demands globally.
Okay, so here's where it gets really interesting, and I think this part demonstrates the immense velocity of execution in this sector.
Yeah, this is a key finding.
The roadmap's baseline review, it reveals a stunning success story. Targets that were set back in the predecessor document, Roadmap 2.0 for 2025, they weren't just met.
No, they were largely surpassed.
And by 2024, that's rapid, ahead of schedule execution. It feels like it confirms that world-class capability is already established.
The data is undeniable, especially in the hybrid dedicated engine or HDE space.
Let's get into the specifics.
Okay, let's look at the overachievements, because they represent a major shift in the global technology hierarchy. For hybrid dedicated engines, so that's the specialized combustion engine designed to run only in the most efficient zone of a hybrid system, the maximum thermal efficiency target for 2025 was set between 42 and 44%.
Which was already ambitious.
Very ambitious. The actual results achieved in 2024, they hit 46.5%.
Hang on, let's just pause on that number, 46.5%. For our listener who might not live and breathe powertrain physics, can you explain the sheer magnitude of achieving just 1 percentage point gain at that kind of altitude?
It's a fantastic question. It's not about one massive breakthrough.
It's not a single silver bullet.
No. Once you get past 40% thermal efficiency, every single decimal point is a battle against the fundamental laws of thermodynamics. So achieving 46.5% doesn't rely on one thing. It's the successful, synchronized optimization of thousands of factors. Friction reduction, combustion stability, sophisticated cooling, advanced air management, precision fuel injection.
The whole system.
The whole system. And when you consider that most standard gasoline engines are still hovering around, 35% efficiency? 46.5% is a genuinely world-leading engineering achievement, and they crushed it a year ahead of schedule.
And it's not just the engine level, right? We see similar overperformance at the system level, too.
Absolutely. The hybrid system, WLTC, that's the Worldwide Harmonized Light Vehicles Test Cycle Efficiency, its target was 83% for 2025. The 2024 actual achievement was 89.4%.
So almost 90%.
Almost 90%. This means the entire system engine, motor, battery, transmission is converting gasoline energy into motive power with almost 90% efficiency on a typical cycle. And the non-hybrid engines saw success too. Heavy-duty diesels reached the 48 to 49% maximum thermal efficiency range, successfully meeting their 2025 goals as well.
So what's the tactical explanation the report gives for this overwhelming success, especially in the hybrid sector?
The report attributes this success directly to strategic choices within the domestic ecosystem. First, the choice to use plug-in hybrid systems, PHEVs, as the primary breakthrough vehicle, with a focus on electric drive predominance.
So letting the electric motor do most of the work.
Exactly. This allows the HDE to operate predominantly in its narrow, highly efficient sweet spot. And second, the rapid, innovative development of multi-mode dedicated hybrid transmission, or DHT, topologies.
A DHT. That's basically a specialized transmission that cleverly couples the engine and motors to allow for multiple operating modes. Pure, EV, series hybrid, parallel hybrid, all in one unit.
Right, precisely. And these DHT innovations, combined with core engine advancements like super high compression ratios, up to 13 to 16 to 1, the adoption of the high-efficiency Atkinson-Miller combustion cycle, and the electrification of engine accessories.
All that together.
All of it together allowed them to harvest previously untapped efficiencies simultaneously across both the power source and the transmission structure.
And this successful execution, it fundamentally alters the competitive landscape. It sounds like domestic brands have shifted from being ambitious challengers to really setting the technological pace, particularly in passenger vehicles.
That is the defining narrative of the past 2 years. Historically, undisputed hybrid expertise belonged to established foreign leaders like Toyota and Honda.
Of course.
But current data shows a clear reversal. In 2024, domestic HDE thermal efficiency figures, you have GE citing 46.5%, BYD citing 46.06%. They surpassed the publicly cited figures for those established competitors like Toyota at around 41% and Honda at 40.6%.
So this isn't just closing the gap.
No, this is evidence of technological supremacy in the most complex, high-efficiency part of the hybrid domain.
And the innovation here is architectural. I love this analogy the document uses. It's a bit provocative. 100 flowers blooming regarding the DHT transmission topologies.
It's a perfect and I think necessary analogy. While traditional leaders like Toyota or Honda largely stuck to a single power split configuration, which was the recognized gold standard for years, the Chinese sector innovatively developed a multitude of different architectures all at the same time.
So what are we talking about?
We see highly focused one-speed DHTs, 2 speeds, 3 speeds, even 4 speeds from different major manufacturers.
But isn't that strategically risky? Traditional giants stick to one core proven system because it simplifies the supply chain, manufacturing, development costs. Does this diversity, this 100 flowers blooming, suggest chaotic development or genuine architectural superiority?
That's a critical challenge to raise. In a purely academic sense, yes, it might look fragmented, but the strategic intent is clear. Rather than just perfecting one established solution, they are exploring the entire solution space. This diversity represents a fundamental strategic shift.
From what to what?
from solving established engineering problems to creating entirely new topologies that are customized for different application scenarios. An urban PHEV versus a long-range REEV.
So it's about optimizing the architecture to fit the need.
Right, rather than forcing the need to fit the architecture. It's the mark of a system transitioning from chasing benchmarks to creating them, even if it carries the short-term risk of manufacturing complexity.
Now, every honest consultancy report has to highlight the weaknesses, and here we pivot to the commercial vehicle, or CV, shortfall.
Right.
Hybridization in massive trucks and buses is lagging significantly behind the passenger car success story.
It is a noted vulnerability, and it reflects the much higher hurdle that heavy-duty applications face. Currently, commercial vehicle hybrid development relies heavily on simpler, parallel HEV systems, often utilizing advantages inherited from foreign automatic transmission technologies.
So unlike passenger cars, where the hybridization drive is robust and diverse, widespread adoption in commercial vehicles is still heavily contingent on external factors.
It is.
Meaning, what specific factors are stalling the adoption of hybrid trucks?
It relies heavily on evolving regulatory frameworks for energy consumption limits, and crucially for fleet owners, the total cost of ownership, or TCO.
TCO is everything for a commercial operator.
It's everything. For an operator running massive fleets 24/7, TCO is the only metric that matters. And the engineering difficulty is immense. Regenerative braking, which is a key efficiency tool in passenger cars, is far less effective in a heavy-duty truck.
Their duty cycles are totally different.
Totally different. They prioritize reliability, predictability, and sustained torque, not quick acceleration. So if the hybrid premium doesn't translate into massive, reliable fuel savings that overcome that higher initial investment, adoption just stalls.
So what does the roadmap say needs to happen?
It acknowledges that technical breakthroughs are urgently needed, particularly in dedicated hybrid systems for heavy-duty applications, to create that compelling TCO argument, especially through component durability and efficiency gains that compound over, say, 1,000,000 kilometers.
Okay, so that dual reality excellence in cars, a strategic gap in trucks, that sets the stage for the 2040 long-term vision. And the future is defined by these four core pillars, the four modernizations, which elevate this strategy far beyond just simple performance metrics.
Yes.
These pillars define what global leadership is supposed to look like in 15 years.
And these four pillars, high efficiency, integration, intelligence, and globalization, they're the governing principles for every single technical task between now and 2040. They shift the focus from component-level optimization to system-level lifecycle optimization.
Let's start with high efficiency. Again, this sounds obvious, but the definition in the roadmap goes way beyond just achieving 50% thermal efficiency.
Indeed. The definition of high efficiency here is rigorous and demanding. It means ensuring that all power sources, the internal combustion engine, the dedicated hybrid engine, the electric motors, operate full-time and under all operating conditions within their absolute most thermodynamically efficient zone.
So the pursuit is continuous.
It is. Improving system efficiency across every conceivable driving scenario, achieving perfect conversion and precise control of oil-to-electric energy conversion, and minimizing parasitic losses down to the last millijoule.
So it's not enough to hit 50% on a test bench in a lab. The goal is to maintain peak efficiency or something near it in complex, real-world driving environments.
Exactly, like urban traffic or climbing mountain passes. It's the pursuit of perpetual controlled efficiency, realized through advanced control software that ensures the engine is always in the absolute sweet spot, regardless of what the driver is demanding at that moment.
Okay, pillar 2, integration. Traditionally, integration just means making components smaller, consolidating functions into a single casing. But here, the roadmap suggests something much more complex, focusing on systems coupling.
This is a sophisticated and truly forward-looking vision of integration. It does demand innovative topology and structural design, leading to extreme component consolidation, yes, reducing axial length through gear nesting and multi-component fusion.
But that's not the main point.
No. The critical cutting-edge element is the strong correlation and coupling between the power domain and the chassis domain.
Okay, what does coupling the power domain with the chassis domain actually mean in terms of how the vehicle moves?
It means the powertrain is no longer just a disconnected engine block and a gearbox. It becomes a unified motion control system that's dynamically linked to how the car handles, brakes, and moves.
Can you give us an example?
Sure. Instead of the braking system being independent, the powertrain has to coordinate instantaneous torque fill from the motor with the combustion engine's output and the car's stability control systems, all in real time. The power unit has to be flexible and modular enough to allow for customized application scenarios, heavy truck or light passenger car, while operating as one single digitally controlled domain.
Which brings us to pillar 3, intelligence. This is arguably the most transformative one, moving us away from fixed, rule-based systems. It suggests the powertrain itself has to learn and adapt.
Absolutely. Intelligence is defined by the deep integration of big data and large models across the entire life cycle: design, control, and maintenance. The report notes that older, rule-based systems often led to high real-world fuel consumption because they just couldn't account for variability. Now, the mandate is dynamic, predictive optimization.
Let's deep dive into the key concept here. The future control paradigm is described as customized, globalized, and self-evolving strategies. And this culminates in the 1,000 people, 1,000 cars, 1,000 faces model. What does that actually sound like on the road?
It's personalized energy management on an immense scale. Imagine a system that in real time is processing multiple inputs: static data like map topography, known inclines on the route ahead,
Right.
dynamic traffic information, the specific driver's profile, so their past acceleration habits, their preferred speed, and then large-scale cloud platform data about battery degradation or optimal thermal control. It uses all of this multi-source input to match the ideal power output and energy recovery logic continuously.
So if I'm driving aggressively because I'm late for a flight, the car is using big data to say, okay, this driver prefers responsiveness over maximizing fuel efficiency for this particular 10-mile stretch. Let's hold the battery charge high for maximum electric boost.
Precisely. And the person behind you, who's just gently cruising to the market, gets maximum coasting benefit, and the system uses the engine very sparingly.
Yeah.
The control strategy moves from being merely reactive to being deeply predictive based on the context of the environment and the driver's historical data.
And it's self-evolving.
Crucially, it's learning from millions of other vehicles and feeding that learning back via over-the-air updates, constantly optimizing energy utilization for your specific vehicle on your route with your driving style. It's an AI layer managing the physics layer.
And the final pillar, globalization, brings us back to the main strategic objective. This is the payoff, not just technical superiority, but market and brand dominance.
Globalization is the strategic definition of success. It requires achieving autonomous innovation in all critical core technologies. The mission is to establish a stringent global quality certification system, elevate domestic brands to international recognition, and ultimately supply the world with high-cost performance products.
So it's about setting the standard.
Yes. The document explicitly positions the achievement of this efficient powertrain system as the crucial marker for the industry's success in leading the globalization effort. They aim not only to compete, but to set the international standard against which others will be measured, both technically and in terms of quality and cost.
Okay, so to transition from today's world-class baseline to that 2040 vision, the roadmap provides a phased, highly quantitative blueprint.
Yes, and we can think of these three phases as building blocks. Each one focuses on a specific technological layer: first hardware, then software, then full autonomy.
So phase 1 is the immediate sprint from 2026 to 2030, focusing entirely on maximizing the foundational component technology, the hardware extremes.
This phase is brutal. That's all about pushing the physical hardware, the combustion, the materials, the pressure to its thermodynamic and mechanical limit before the software layer really takes over.
What are the must-hit quantitative targets for this initial sprint by 2030?
For hybridization, PHEV and HEV dedicated engine efficiency has to hit 45%. And range-extended EV engines, which can operate more consistently at their peak, must reach 48%.
And for the big trucks?
For heavy-duty commercial vehicles, the non-hybrid diesel engine has to reach a massive 51% maximum thermal efficiency. And for system efficiency, heavy-duty CV systems must hit 85% CHTC efficiency, which represents an 8% fuel savings over the 2024 baseline.
And the key technical tasks, the hardcore engineering breakthroughs required to hit these phase 1 numbers.
It's pure mechanical optimization and thermodynamic manipulation. They are tasking HDEs to break through compression ratios exceeding 17:1. And crucially, mastering sparse combustion with a lambda greater than 2.0 is mandated.
Wait, sparse combustion, lambda greater than 2.0.
Yeah.
Can you quickly define that for us? Is that another way of saying an ultra-lean fuel mixture?
That's precisely right.
And what's the engineering challenge of keeping a flame lit when there's barely any fuel present?
Well, you hit on the core problem. Lambda refers to the air-fuel ratio. Lambda equals 1 is the chemically ideal stoichiometric ratio. Lambda greater than 2 means you have twice as much air as you need. It's a fuel-starved or sparse mixture
And it's more efficient because.
because you lose less energy to heat waste. But the challenge is ignition stability. If the mixture is too lean, the flame just extinguishes, or you get misfires and excessive NOx emissions. To solve this, you need extreme precision control and often extremely high compression ratios, like that 17-to-1 target, and massive fuel injection pressure to achieve instantaneous localized combustion.
Speaking of pressure, they target 500 bar rail pressure for gasoline direct injection systems. That sounds enormous.
500 bar is an enormous amount of pressure. To give you some context, that's roughly 7,250 psi. It's about 25 times the pressure in a typical road car tire.
And forcing fuel spray at that pressure is difficult to do reliably.
Incredibly difficult. You need injectors and pumps that can sustain those pressures for hundreds of millions of cycles without failing, all while atomizing the fuel so perfectly that it ignites cleanly in that sparse combustion environment. This is a massive materials and manufacturing hurdle.
And for the CV engines in this phase.
For non-hybrid commercial vehicles, the Phase 1 focus is similar. Mastering ultra-high combustion pressure, extremely high-pressure injection, and advanced variable valve technologies. And on the hybrid system side, it's about achieving high integration and optimal multi-power source matching to efficiently use those newly maximized engines.
So once that robust hardware foundation is solidified in Phase 1, Phase 2, from 2031 to 2035, seems to be the critical inflection point where that intelligence pillar really takes hold.
It is.
This is the shift from mechanical muscle to digital brainpower.
It is the software and systems leap. By 2035, the quantitative targets reflect this push toward software-enabled optimization. So PHEV efficiency moves to 46%, REEV HDE targets 49%, and heavy-duty diesel pushes all the way to 54%.
And the CV system efficiency.
It aims for 86% CHTC, realizing a 13% savings compared to the 2024 baseline. And you'll note the rate of progress slows a little in the HDE numbers because the subsequent gains get much harder, and they require software to unlock the hardware's full potential in real-world use.
The key tasks certainly shift dramatically from mechanical hardening to smart operation.
Precisely. The smart leap involves several technological breakthroughs. HDEs must break through to ultra-sparse combustion with a lambda greater than 2.5. Now we're talking about extremely lean mixtures. And the data systems come in here. Critically, this phase mandates the development of cloud platform big data systems to enable highly efficient energy storage and utilization. The energy management goal is no longer just good, it's about achieving near global optimal energy management across diverse driving scenarios.
That near global optimal control, that's where the Thousand Faces model really comes into its own, using predictive data rather than just reacting to the accelerator pedal.
Absolutely. The system is starting to think ahead. And mechanically, there's a simultaneous focus on reducing frictional losses, developing non-contact sealing structures, and smart precision lubrication for transmissions and axles. The mechanical integrity has to match the digital precision.
Okay, so that brings us to Phase 3, the long-term goals, from 2036 to 2040. This is the grand finale. This is about securing technological sovereignty and achieving a complete market transformation.
It is.
And by 2040, what's the mandatory market penetration goal for traditional energy passenger vehicles?
The ultimate market ambition is that traditional energy passenger vehicles must achieve 100% comprehensive hybridization.
Wow.
It's a declarative statement. The era of non-hybrid internal combustion engines in new passenger cars is targeted to end by 2040 under this plan, moving all conventional vehicle sales into high-efficiency hybrid categories.
And the quantitative targets here are truly headline-grabbing, particularly breaking the ceiling on internal combustion engines.
Yes. PHEV HDE efficiency targets a rigorous 48%. But the landmark, the symbolic target, is for the REEV HDE, achieving 50% maximum thermal efficiency.
50%.
50%. This breaks that symbolic barrier for series hybrids, and it represents a thermodynamic achievement that redefines the combustion engine's perceived efficiency limit.
And for the big trucks?
Heavy-duty diesel pushes to 55%, with CV system efficiency reaching 87%, realizing a remarkable 16% total savings versus 2024.
Let's talk about the physics. How do you actually get a combustion engine to that kind of thermodynamic purity? What are the key technological tasks for this sovereignty drive?
They're about mastering the most complex, high-value technologies that require ultimate IP control. For HDEs, this includes variable compression ratio, or VCR technology.
And what does VCR do?
VCR allows the engine to dynamically adjust its compression ratio on the fly, optimizing ignition for every single load condition, so low compression for high power and ultra-high compression for maximum efficiency. It's like having two different engines in one.
And what about cylinder linerless technology? That sounds like a radical redesign of the engine block itself.
It is. A conventional engine uses a steel sleeve or a liner inside the aluminum block. Removing that liner improves heat transfer, which is crucial for managing the extreme heat from VCR and high-pressure combustion. It also significantly reduces weight and complexity, though it places immense demands on material science and manufacturing precision.
So you often need advanced thermal barrier coatings internally.
Exactly, to manage the heat.
The systemic goal is also defined here. The deep fusion of the power domain, the chassis domain, and the smart driving domain. This moves the car beyond simple energy management to fully intelligent vehicle motion control.
Exactly. And the final piece of the 2040 vision, which underpins that globalization pillar, is clearly defined. Completing autonomous innovation for core components, including chips, high-precision sensors, and actuators.
So this directly addresses that strategic vulnerability we highlighted earlier in the CV sector.
It has to.
Technical leadership can't be sustained if the brains of the control system, the microchips and the sensors that detect the ultra-lean combustion, rely on foreign IP and a vulnerable global supply chain.
Right.
So this final phase isn't just about making better engines, it's about industrial security and sovereignty.
That's the strategic core of the whole roadmap. Hitting 50% thermal efficiency is meaningless if the control chip you need to maintain that hyper-precise lean combustion cycle is subject to external political pressure or supply halts. The 2040 goal is fundamentally about domestic technological mastery over the entire value chain.
We've established the grand strategy and the three phases. Now let's zoom in on the engineering mandate. What specific, non-negotiable quantitative goals are set for the heart of the vehicle, the engine, the motor, the battery systems, that must be hit year after year?
This is where the depth of the roadmap really shines. It demonstrates that this is not just aspirational rhetoric, but a structured engineering plan. It sets benchmarks for every single subsystem, ensuring that 2040 vision is built on thousands of micro-improvements across the entire value chain.
So starting with the hybrid dedicated engines, the roadmap makes a key functional distinction between the PHEV/HEV engines and the RDV engines. Why the different efficiency targets for those two?
It's all defined by their operating cycle. A PHEV or HEV engine has to perform a dual role. It generates power, yes, but it also frequently participates directly in driving the wheels, especially at higher speeds.
So it needs a broader, efficient operating range.
Exactly. In contrast, the REEV engine focuses almost purely on high-efficiency power generation. It runs constantly at or near its peak efficiency point, just to charge the battery. It rarely drives the wheels directly. It's a specialized generator.
And that's why the max thermal efficiency target for REV engines in 2040 is that higher symbolic 50% figure?
Correct, compared to the 48% target for the more functionally complex PHEV and HEV engines.
And the technical pathways to hit these numbers are aggressive, requiring that advanced thermodynamic manipulation we talked about, like VCR and thermal barrier coatings?
Absolutely. By 2040, both pathways are aiming for these core breakthroughs. VCR is key to managing the extreme efficiency demands across different loads. Thermal barrier coatings and linerless technology fundamentally alter the engine block structure to better manage the immense heat generated by ultra-lean combustion and higher pressures, while also reducing frictional losses and weight.
And that extreme 500 bar rail pressure we discussed earlier, that's the non-negotiable fuel system target for gasoline engines to ensure better atomization.
Yes. Better atomization, improved mixing, and therefore cleaner, more complete, and ultimately more efficient combustion. It's essential for stable ignition in those sparse, lean burn environments.
Okay, let's move to the drivetrain itself. The dedicated hybrid transmission, the DHT, and the mechatronic coupling unit. This is where system efficiency is won or lost due to frictional losses.
And the targets are set very high for mechanical efficiency and density. By 2040, the roadmap demands maximum mechanical transmission efficiency of greater than 98%,
98%.
meaning less than 2% energy loss in the gearing, and a torque-mass ratio greater than 48 newton meters per kilogram. This reflects an intense focus on extreme lightweighting alongside minimal friction.
How will they achieve these high mechanical targets in the gearbox? Are we talking about entirely new manufacturing processes?
We are. It's a combination of innovation and manufacturing precision. First, continued focus on developing advanced multi-gear, multi-mode DHT topologies customized for different vehicles. Second, achieving highly integrated designs.
So that means multi-component consolidation, reducing length through things like gear nesting.
Right, sharing components and using high-strength, lightweight materials for the casing. But crucially, to hit 98% efficiency, they have to shift to extremely precise manufacturing high-precision grinding processes, utilizing low viscosity, smart lubricants, and adopting low-drag, non-contact sealing structures to eliminate nearly all parasitic losses.
Okay, now for the intelligence layer, the motors, batteries, and control systems.
Right, and the performance ceiling for the entire hybrid system is defined by how well the electrical components can handle and convert energy. This is the domain of semiconductors and advanced materials.
Let's start with motors and controllers. We're seeing a big push for wide bandgap semiconductors, particularly silicon carbide, or SiC.
SES is the absolute state-of-the-art for power electronics. It handles higher voltages, higher temperatures, and it swings faster than traditional silicon. So the roadmap highlights the goal of SiC controller peak efficiency reaching greater than 99.7% by 2040.
99.7%. I mean, that is virtually perfect. For those of us who appreciate engineering difficulty, operating in the 98 to 99% range is hard enough. What does chasing those last 0.3% even involve?
It involves pushing materials science and packaging technology to their absolute limit. It's about minimizing resistance in every single circuit trace, perfecting cooling to prevent thermal resistance, and reducing the switching losses of the power module itself.
But that tiny efficiency gain is massive in the real world.
It is, because less heat waste means smaller, lighter cooling systems, which in turn reduces vehicle weight and improves overall range.
And for the motor itself, what physical benchmarks must be met to keep pace?
The motor mass torque density has to exceed 19 newton meters per kilogram by 2040, which is up from the current goal of around 16. So significantly more power for the same volume and mass.
And that generates a lot of heat.
A lot of heat. So to manage it, advanced cooling techniques are mandated. Oil cooling, composite cooling, and real-time intelligent control of high-capacity electronic pump cooling systems are crucial to keep those expensive SiC modules happy.
Batteries are equally critical. What density leaps are planned for HEV and PHEV cells?
The roadmap sets ambitious and distinct goals. For HEV power-type batteries, those focused on high power output for short bursts, the target is a mass energy density greater than 140 watt-hours per kilogram.
Okay.
For PHEV and REEV batteries, which need to deliver both power and longer range, the target is a highly demanding mass energy density greater than 350 watt-hours per kilogram by 2040.
That's a huge jump in energy storage. We're moving into the territory of what are considered next-generation chemistries today.
We are, and the plan explicitly includes active research and demonstration applications for new battery systems, like solid-state ion batteries, which promise higher safety and energy density, and sodium-ion batteries, which demonstrates a strategic hedge against relying solely on current lithium chemistries and imported materials.
And there's a deep integration of intelligence here, too.
Yes, smart thermal management using liquid cooling and phase change materials, plus customized self-maintenance features via cloud updates and OTA for things like mechanical abuse monitoring and fatigue pre-warning.
All of these components lead to the brain of the vehicle system integration and energy management. How does that intelligence pillar manifest in the control strategy's evolution through 2040?
The control strategy has a clear, phased evolution. It moves from personalized adaptive control to global optimal control by 2035, achieving that near global optimality across driving scenarios. And finally, culminating in vehicle energy interaction synergistic control by 2040.
What does that mean, synergistic control?
It means the car isn't just managing its own energy anymore. It's actively interacting with external factors, traffic, cloud data, predictive maintenance schedules, maybe even vehicle-to-grid information, for truly synergistic control of all motion and energy flow.
And finally, NVH control. If the engine is running extremely lean and at high compression, it risks sounding rougher. Noise reduction has to be a priority.
Noise, vibration, and harshness are critical for premium acceptance. The goal is achieving active, unified NVH control across the entire system engine, motor, and coupling unit. This requires software and hardware coordination to actively cancel out undesirable frequencies.
Is there a hard target?
There is. The specific target is to reduce noise levels in pure electric mode, measured at 1 meter, to under 75 dBA by 2040. For context, 75 dBA is about the sound of a vacuum cleaner. Achieving that low level in a system with mechanical gears and high-power electronics requires exceptional engineering refinement.
Okay, let's shift back to that acknowledged weak spot, commercial vehicles. This sector is heavily reliant on diesel and natural gas, and the goals here are about squeezing every last drop of efficiency out of these high-power, high-mileage machines.
And the targets for CV engines are some of the most thermodynamically challenging because the starting efficiencies are already quite high.
Give us the headline numbers for the big engines.
For heavy-duty diesel engines, the goal is 55% maximum thermal efficiency by 2040. Achieving this requires pushing technologies like extremely high combustion pressure up to 250-270 bar, which far exceeds passenger car norms, and ultra-high pressure injection up to 2500 bar.
And advanced air systems.
Yes, things like electric-assisted turbocharging to stabilize combustion and air intake under those immense loads.
And for natural gas engines, which are often used in urban fleet scenarios.
Heavy-duty NG engines target 54% maximum thermal efficiency by 2040. And the technical pathway involves a major shift in combustion technology, moving from conventional spark ignition towards compression ignition, specifically diesel micropilot ignition.
So you're using a tiny bit of diesel to ignite the natural gas charge.
Exactly. This allows the NG engine to operate with a variable thermodynamic cycle and achieve efficiencies that were previously restricted only to diesel.
We noted earlier the critical gap in the CV supply chain, the reliance on international suppliers for control hardware. Does the roadmap put a clear deadline on achieving domestic realization of these components?
It does. And it's treated as a clear strategic vulnerability that must be rectified. The document notes that international suppliers like Bosch, Fennia, and others still dominate the control software market, and domestic manufacturing of fuel supply and control hardware, including chips, high-precision sensors, and injectors, is lagging.
So if they can't achieve autonomy in chips and sensors, hitting 55% thermal efficiency is almost irrelevant.
It is, because the ultra-precise control systems needed to maintain those hyper-efficient high-pressure combustion cycles would still rely on foreign IP and a vulnerable supply chain. The 2040 target for this sector explicitly includes achieving full autonomous innovation and domestic realization for all core components. It's about closing that strategic vulnerability.
Now, for the transmissions in these massive vehicles, the automated manual transmission, the AMT, remains dominant, but efficiency gains are still required.
The goals for AMT focus on optimizing mechanical design and control. By 2040, heavy-duty transmissions must achieve efficiency greater than 97.8% and a torque mass ratio of 13 Newton-meters per kilogram.
And the techniques for that?
Using low drag, high precision machining, low viscosity oils, and developing customized transmission structures that might eliminate components like synchronizers entirely. There's also a mandate for utilizing full simulation technology, or digital twins, for dynamic and fatigue analysis to accelerate the development cycle.
And finally, the drive axles. These are massive components, and even a fractional efficiency gain will compound rapidly over a truck's lifespan.
And the drive axles must hit single-stage efficiency targets greater than 98.5% by 2040. The focus is dual: reducing friction through intelligent lubrication control and precision gear design, and lightweighting using hollow half shafts and aluminum alloy casings.
And the emphasis on maintenance is a direct TCO indicator.
It is. They're targeting extending oil change intervals to massive lengths between 800,000 to 1 million kilometers. This durability goal confirms that the plan is not just about lab bench efficiency. It's about delivering globally competitive, robust commercial products.
Okay, so if we summarize the overall narrative here,
Right.
What's the big picture?
The big picture is that this document is a comprehensive, phased strategy for achieving total industrial sovereignty and technological leadership in powertrains. It is highly quantitative, it is deeply committed to a hybrid-centric future, even for large trucks. And it's structured with clear, measurable phases leading to total technological autonomy in critical, high-value areas like VCR engines, Seeker controllers, and control chips.
So what does this all mean? The roadmap clearly shows the industry has transitioned from achieving world-class technical strength, which that 2024 data on PHEVs already confirmed, to actively pursuing global leadership.
That's right.
And that final transition, it hinges entirely on successfully executing two critical interconnected phases: the intelligence integration, the software layer, and the predictive big data, and most critically, achieving core component localization, the chips and the sensors.
Without achieving true autonomy in those latter two categories, leadership remains strategically vulnerable.
I agree completely. This detailed roadmap presents a clear technical path to market dominance, driven by rigorous engineering targets and a strategic focus on efficiency and hybridization.
However, and I think we have to close by recognizing this, the final realization of that 2040 vision, particularly the twin goals of globalization and autonomy, might be influenced less by the genius of the engineers breaking the 50% thermal efficiency barrier,
And more, Bar.
and far more by the complex external forces of geopolitics and global supply chain dynamics. If international standardization bodies resist new dominant technical protocols, or if global trade policies shift rapidly, how much can pure engineering prowess achieve? What other factors outside of engineering, be they material access, currency fluctuations, or shifts in major consumer markets, might accelerate or derail a plan this ambitious?
And that's the strategic question that remains.
It is, once the blueprints are finished and the focus shifts from the drawing board to the global marketplace.